You guys just wait for a while. Okay, let's go now. Okay. So now we want now to see how we can be able to analyze the steady state error for different cases. So we have our transfer function, which is equal to g of s. So g of s must have at least one pole which is equal to 0. So if one pole is equal to 0, that means the denominator of the system will be equal to 0. So we'll have our g of s will be equal to infinite. But remember that for us to get, can be different cases where a pole can be equal to 0. So that's why we want to analyze different cases. We say n is bigger or equal to 3. So we are going to see different cases with different value of n. So that's gonna help us to understand. Let me check. I think there's someone who stopped the recording. Let me check. No, it's okay. It's okay. So, okay. So we want to analyze a case where we have different value of n. So this is the first case where we consider the system with no integrator. So I told you that the integrator is 1 over s, but that 1 over s is different to the input because we talk about the 1 over s, which is, so it does mean where we have s with power to 1. So s is on the transfer function, not on the side of the input. Are we together? Hello, guys?
Yes.
Okay,
Yes.
so now we want to analyze this system where the input is 1 is the ramp, and we need to find the steady state error of this system here. So the input now, it's a step function which is equal 5 ut is and which is equal to 5 over s. So now we want to use this system with this input to find the steady state error. Let's try to solve it together. Okay, so we can see here they give us already saying that when we apply this formula, I think we know where it's coming. It comes from. Guys, let me just stop sharing. Then I can restart so I can have those tools to explain with. Okay. So now, remember, I think all of you understand where this is coming from. It's just the formula of the steady state error. So now let's see what is happening on this side, because this one we have jumped some steps. So on this side, what we have is the numerator is 120 s plus 2 s plus 3 over s plus 4. Okay. So we have here 120 s plus 2 over s plus 3 times s plus 4. Okay, so this is what is on this limit. So limit 0, a limit of s approaching 0 of this one. So we know that when we put 0 here, so we'll have 0 there. So it's going to be 120 times 2. It's going to be 240 over what? Over this is 3 times 4. So it's going to be 12, right? So this is going to give us 20. So this is going to be 20. 1 plus 20. Because this value here is 20. 1 plus 20 is going to be 21. Then, because everything is under this 5, it's going to be 5 over 21. Are we together, guys? So this is how we find.
Yes, sir. Yes, sir.
So this is in the case where the input is the step function. Let's now see where we have the input, which is a ramp function. So 5t u of t. So the now r of s will be equal to 5 over s square. So in that case, you can see that if it is equal to 5 over s square, simplifying this one will remain with 5 over s. So that s gonna be times this g of s, and we will have this one won't exist anymore because it's going to be replaced by it's going to be this times, and the limit of 0 is going to be equal to 0. So we'll have this one 5, and when we try to solve as we solve there, we'll have let's say, yeah, it can have 20, but this one gonna be times 0 because there is a 0 there. So the limit will be equal to 0. So we'll have s over 0. That's gonna give us infinite. So this is this gonna be the steady state error for the ramp function. Remember, we are in the case with no integrator. That means the s on the denominator of the system is equal to 1. So there is no s there. So this is what this one. So there is no any s here. It means that we have s our n is equal to 0. Then s exponential 0 is equal to 1. So in the case where n is equal to 0, so we don't have any we don't have steady state error in the case of ramp and in the case of parabolic. So let's now see another example with one integration. So we have one integrator, so which is s there. So it means that n is equal to 1. Okay. So now by solving this one, let's apply the 5 over s as the input, so which is our step input, 5 over s. We apply it to this system now. Let's see what is going to happen. So by applying this one now, as you can see, we have the same thing here. This s and that s is going to cancel themselves. Then we'll have 1 plus limit s approaching to 0 of g of s. So now you can see that when we try to replace this one, let's go back to the system here. So when we're using this one here, g of s, what are you going to have? We'll have a limit of this one. This is gonna give 0. This is gonna give us 200 times 6. It can be 1 point something. But remember, we have s here on the denominator. This is our integrator, so it's one integrator. So s times all this one going to give us 0. So 100 to 1,200 over 0 is going to give us 0. So that means now this term here will be equal to infinite. So 5 over infinite is equal to 0. Are we together, guys? Or there's any question here?
No.
Okay, good. So now let's apply now the ramp input to the same system with one integrator. So we have 5 over s squared. Then when we come here, we're gonna see that this s this we will simplify this one, that one. So we'll have 5 over s, and that 5 over s now that 5 over s, if we apply the final value theorem, remember we will still have one s because there is s here and there is s Okay, let me try to write it so we can see. Okay. Let me try to write this one is 100 s plus okay. 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 How can I write it? So it's, let's say, hundreds s plus memory has become bad. S plus 2, s plus 6, s plus 3, s plus 4. Okay. Okay. S plus 2 and s plus
S plus 6.
6. Okay. Over
S into S plus 3.
s plus 3,
S
then
plus 4.
s plus 4. Okay, good. So we'll have this one here. Then this will be the okay. This will be the formula of the error. Now remember, our input and this s is going to cancel themselves. So now when we apply this s that's going to remain here, remember this s here is going to be times this s of g. Then we can simplify this s and that s, so we can replace the value. We're going to have something like let's try to see what is happening here. So we have 100 there. That's going to be 100 times 2 is 200. It's 1.2. Then here we're going to have 12, right? Are we together? So it's going to be 100. It's going to be this 1,200. I think so, over 12. So this is going to give us 100, and that's what we have here. Okay, are we together? Are we together, guys? Or there is any question here?
Yes, sir.
What's the question? What is the question?
You may
There's no
proceed,
question.
sir.
Sorry?
There is no question, sir.
Okay, thank you. Okay. So let's now try to apply now a parabolic. So when we apply the parabolic, we'll find that this is going to be s cube, and this one goes to be s square. So in this case, because there is s square here, replacing the limit is going to give us 0. So the denominator will be equal to 0. So we'll have 10 over 0. It's going to be equal to infinite. So when we have one integrator, we can see that the steady state error for the step function is equal to 0, because our limit is equal to infinite, and the steady state error for the ramp is has a certain value, but there is no steady state error for the parabolic because it's equal to infinite. So let's now see the static error. There is what we call the static error. What is the static error? So this, we are going to introduce different type of the system. I've already talked about that in the previous slide. Now we're going to see it. So we can characterize the unit system by the number of integration, which is n, the one I show you in the forward path open loop system. So now we have this one. You remember this this equation I showed you exactly before, something like this. So we have n. N is giving us the number of integration. As I told you, in most of case, n is equal to 0, 1, and 2. So that is the common case that we can find. So so n, it's already giving us the type of the system. So once you know the value of n, you can define which type of system that we have. So now let's see if n is equal to 0. If n is equal to 0, now we have limit of s. These parameters, it's equal to what we call kp, which is the position constant. In that case, when n is equal to 0, this is how you can find your steady state error. It's 1 plus 1, so it's 1 over 1 plus kp. So this limit here, it's kp. This is also called a DC gain. Okay, it's also called a DC gain. So just by knowing DC gain, we can be able to quantify the error of the system. So this kp is called a DC gain, is also called a position constant. Position constant. So this limit is a DC gain. It's also called a position constant. In the other term, this limit here is what we call the static error. Okay, the static error constant. So now we call position only in the case where n is equal to 0. That's what this kp is called a position constant. Is when n is equal to 0, we talk about kp, the position constant. But this limit as g of s in general is called the static error. So now we can also quantify the steady state error just by using a static error, which is this limit s to 0. By knowing this one, so we can also say we are in this case or in this case. So now let's see for the second one. So with the static error, so when we have a static error equal to the position constant, so it can track unit step with non-zero error. So in this case, we can have a unit step as an input, and the error will be different to 0. You have seen it before, and but we cannot track the parabolic and the ramp input. So now let's see when f is equal to 1. So when f is equal to 1, we are in this case here. Remember, when n is equal to 1, in the case where we have one integrator, so we end up by finding this this formula on the previous one. So that means we have 1 over kv. In the case where n is equal to 1, the static error is called kv, which is the okay, so it's a velocity position. So it's there for the velocity. So we have 1 over kp. So this one can track. In the case we have kv, we know that the steady state error is equal to 0 for the step input, but is equal to a certain value different to 0 for the ramp, but it cannot track the input because in that case also the steady state error is equal to infinite. So now kv is the velocity constant. Let's call velocity constant. Let's call it. So now we have the case where n is equal to 2. When n is equal to 2, that means we have 2 integrator in the system. So this is how the steady state error formula is given. So, and the 1 over Ka, this Ka is called a acceleration constant. So now, this can track, yes.
So I'm kind of lost. Can you please explain again the position constant?
The position constant.
Yes, sir.
Okay. Let me try to go a little bit back because this is gonna help you to understand. Okay. You remember this example, right?
Yes, sir.
Yeah. Okay. So when I introduce this example, let me go back to this. Where is it? So let's go. Okay. When I introduced this example, I was talking about this. I was talking about this system with no integrator. You remember? I say the
Yes.
the integrator. The number we are integrating the system. Then I say we can quantify it by the number n. Remember, we say n is less than 3, less or equal to 3. Then we say in most of case we are using 3 type of integration: 0, 1, and 2. Then I say when we have this example, because there is no n integration here, it means that our n is equal to 0. When n is equal to 0, after applying a step function, this is what we are getting as a okay. After applying a step function, we are getting this equation for the steady state error, which is 1 plus limit s approaching 0 of g of s. This is what we are getting. And by getting this one, we will have an error which is going to be different to 0, but we will have an error. But in the case where we don't have integrator, when we apply a ramp, this is where we apply the ramp. By solving, we'll find out that the steady state error is equal to infinite. That means with the ramp, we cannot track the error. But with the step function, we can track the error, which is going to be equal to a value which is different to 0. Then we use now a system with one integrator, which is S, this one. That means N is equal to what? Is equal to 1. So we have one integrator. So by solving this problem, by applying different input like the step, ramp, and parabolic, so by applying the step, we find out that the error in this case is equal to 0. So this is what, when we apply the step, the error is equal to 0. And we said when we apply now a ramp, the error is giving us a certain value which is different to 0. So now when we have when n is equal to when n is equal to 1, we have error for the ramp and error which is equal to 0 for the step. But for the parabolic, we cannot track the error because it's equal to infinite. Then now we want now to quantify the type of system, or in terms of n. Then I say n in terms of n, of the number of integration. So when we integrate once, twice, or many times, then we say, okay, now we are going to consider n like the value of n will be equal to 0, 1, and 2. So this, just knowing by the value of n, we can talk about the type of the system. So let's now go here. We say when n is equal to 0, remember the example we solved then where we didn't have n integration. This is how the steady state error equation or formula is given to us. Now, this term here, the limit s approaching 0, which is called the static error. This is calling the static error. So we are going now to say, okay, in the case where n is equal to 0, we have the limit of the transfer function is called now a constant position, or position constant. This is Kp. Now we replace this one by Kp. So when your n is equal to 0, this limit is called constant position is Kp. Are we together?
Yes, sir.
Okay. Then when we have KP, what is happening? When we have KP, we can find the error for a step input, but that error is going to be different to 0 when we have KP. So that means n is equal to 0. But we cannot track or find the parabolic because they are equal to infinite. So now we say when n is equal to 1, what is going to happen? When n is equal to 1 now, we call this term here the static error limit s g of s. Now we call it kv. In the case n is equal to 1, this kv now is the velocity constant. Are we together?
Yes, sir.
Yeah, and the formula of the steady-state error will be now 1 over kv. Where kv is equal to limit of s approaching 0 sg of s. So we call it kv. And in this case, the steady-state error for the input, which is a step function, is going to be equal to 0. And the steady state for the ramp is going to give us a value which is going to be different to 0, but we cannot track the parabolic input. So for the parabolic input, the steady state error is infinite. So now we move to the next case where n is equal to 2. In that case, we can also try to find, we know that now when n is equal to 2, this is how the limit is going to look like, and this is calling the acceleration constant, and the steady state error must be calculated by k over a. Then with that one, when we apply the step, the error is going to be equal to 0, and the ramp also is going to be equal to 0. So the step and the ramp are giving us 0, but the parabolic is giving us a certain value, a certain error which is different to 0. So that's what we call the static error constant, which is kp, kv, and kp, kv, and what kka. So now we have kp, which is this limit is our first static error constant in the case where n is equal to 0. And okay, so this is just repeating. So now the steady state error, when we have kp, steady state error is equal to 1 plus kp, and the velocity constant kv. So we have s, and the steady state error is going to be equal to 1 over kv. Then let's move for the acceleration constant. So we know that when we have acceleration constant, the steady state error is going to be E1 over Ka. So we can be able to define whether we are in the position, or we are in acceleration, or we are in velocity, just by knowing the number of integrator, whether if the integrator is equal to 0, so there is no integration there. So we know that we are in the case of Kp. When the integrator is equal to 1, we are in the case of Kv. When the integrator is equal to 2, we are in the case of Ka. So this is the table now giving us different type of system. Type 0, so it's when n is equal to 0. Type 1, when n is equal to 1, and type 2, when n is equal to 2. So, and they say in the case where of type 0, so kp is a constant, kv is equal to 0, ka is equal to 0, and the error, so we cannot track for ramp and parabolic, but we'll have only error for the position or the step for the step input. So, and when we are in type 1, it means that we will have error different to 0 for the ramp, and 0 for the kp, and infinite for the ka. And in this case also, we know that the Kp is infinite, Kv infinite, K is a constant, so we'll have zero error. So the error will be equal to zero for the step and the ramp, and for the parabol, we'll have a certain value. So now let's see an example, then we're going to finish by there. So this will going to be the end of this chapter. And I think by Wednesday we'll have time to start now doing the tutorial, and we'll have more session before the 23. We'll see how we pray God for this third wave to be stable, so they can again open the school. Okay, so they say given the control system below, find K such that there is 10% error in the steady state error. So they say the steady state error is equal to 10%, which is I think 0.1. Is it? So the steady state error is a 10%. Now they give us this. They gave us this transfer function and say we need to find the value of K in this transfer function. If you can see already this system here, which type of system we are in? If you can say it. Which type of system is this one? Is type 1, type 0, or type 2?
Type 1.
Type 1. Thank you very much. So we are in the case where we have KV. So we know that, so the error now is going to give us by 1 over KV. That is going to be our steady state error. The steady state error is already given to us. They say it's 10%, so which is 0.1. So we know that 1 over KV is equal to 0.1. So, hello? Okay, so it's just the mic that. Okay,
Hello,
so
sir.
yes. Can
Do
you
we have-
hear me?
Do we have a case whereby we have n is equal to 3? It's even numbers, continuity of even numbers, or odd numbers.
But we can probably have that case, but what will be the input signal in that case?
Where n is equal to 3.
Yeah. So you can try now to solve in that case where n is equal to 3, then you can apply. But remember, we saw that n is less or equal to 3. You remember what we said before?
Yes.
Yes. But you can try to solve it and see what you are going to get. We will probably get something like all the error must be equal to 0. I've never tried that, but I'm sure that they're going to be equal to 0. So you can also try and see what you're going to get. You can apply the parabolic, the ramp, and the step function. Are you going to try it?
Yes. So that
Yeah,
means we'll not have something like that. So we'll have n0, n1, and n2.
Most of the common case we have in, they are just those 3 types. That's why we are. Remember, I told you that in class 2, when we want to define the performance of the system, we apply input, and among them, we talk about the step, the ramp, the parabolic, and there is also a sinusoidal input. Okay.
Okay, please.
Whose phone is ringing there? Please pick up the phone. Sne Temba.
Bandile.
Oh, okay. Good. So in these 6 minutes, I want just to explain this one. So we have this error is going to be 1 over KV, as you said. So that's going to be equal to 0, 1. So we can find the value of KV. So KV is going to be equal to 10. So we have 1 over 0 is going to 10. So now, because we know KV, we can now apply the, we know that KV is equal to limits of S, G of S. You remember it, right? Are we together? Hello?
Yes, sir.
Yeah. So we know that KV, this KV is equal to this one, okay? Then we can say, okay, now this limit of this transfer function is equal to 10. Then we can replace now the transfer function here, and we can solve it. So that's what is going to give us k is equal to 672. Thank you very much. This is easy to solve. You can try also to solve it. The next time we'll be doing the tutorials. Thank you. Have a good day. Yes.
May we please write online for the second test, please?
No, but you know, it doesn't depend on me. It doesn't depend on me. It's going to depend on how things are going to move. If we're still in the same situation, we'll try to set an online test, and we will see how we are going to do it. But I think, are you guys, all of you are used to the blackboard, right?
Yes.
Yes.
So you know how to use blackboard, right?
Yes.
Yeah.
Yes.
Okay, good. So that means the next quiz, you have to submit on blackboard. I will give you the set time and say, okay, you have to maybe to find this problem solving, and you have to submit it in a lapse of time, maybe 30 minutes. After 30 minutes, you want to be able to submit again. So that one will be more serious.
30 minutes.
30 minutes is
Sorry?
little. 30 minutes is little.
Don't be.
We only prepared
It
can't be 30 minutes.
You haven't even
for
seen the question. You say 30
calculations.
minutes is
30
less.
minutes.
It can't
Let's
be.
have got
No,
an
sir,
hour.
it can't.
I'm not talking about the test. I'm talking about the quiz for control
Yes.
practical.
Even though
Still say it can't be 30 minutes.
She'll say.
we need time to calculate. Say we are not
Others are dwelling us.
going to make
Okay, guys, you haven't seen the quiz, so we cannot discuss about that. But it's just an example. I say if the quiz is gonna take long, I will give you more than that. If it's a less, if it's 15, I'll say okay, it's just 15 minutes. Okay.
but so
Okay. Don't make Musindo, okay?
Okay. Thank you very much. We'll meet around 1.
say
Okay.
Yes, we have practical at 1.
Frank, where?
Online.
Online, yes.
Oh, okay.